Suppose that we have a particle in 3D space, so we can show its position using a vector called r. If the momentum of the particle is not along its position vector, it can experience a kind of motion that is like circular motion. And we can associate a kind of angular momentum to this particle, which can be written as r cross p. We can find this cross product using this determinant. The x component of the angular momentum is ypz minus zpy. The y component is zpx minus xpz. And finally, the z component would be xpy minus ypx. In quantum mechanics, position and momentum are operators. So for the three components of the position, we have x, y, and z as operators, and the three operators for momentum are px, py, and pz, and we can write them as minus I h bar d dx, minus I h bar d dy, and minus I h bar d dz. And these are some operators that can operate on state vectors or state functions. We can use the position and momentum operators to write down the components of angular momentum operator. The x component of angular momentum operator is Lx and can be written as minus IH bar y d dz minus z d dy. The expression for Ly, which is the y component of the angular momentum operator, can be written like this. And finally, the last one, the z component of angular momentum, can be written as you see. Pay attention to the pattern we have here. If you want to memorize these expressions, you can just see that after x we have y, after y we have z, and after z we have x. So if we want to, for example, write Lx, we can say Lx is ypz minus zpy. And you can do the same thing for the other ones. And y, after y we have z, and after z we have x. Now let's talk about commutation relations in quantum mechanics. They are very important because we are dealing with operators, and it matters in what order we are using these operators. Sometimes we can actually change the order and it doesn't matter, but sometimes we cannot, and that's where commutation relations are handy. Suppose we have two operators a and b, and we can say this is the commutation relation of a and b. So if they commute, this expression is zero, and it doesn't matter whether we use a first or b, because ab is equal to ba. But sometimes this expression is not zero, and these two operators don't commute. And here, order matters. ab is not ba. For example, the commutation relations for position operators are zero, and they all commute with each other. For momentum operators, we have the same thing. And as you can see, for example, px and py commute. And if you do the same thing for px and pz and py, you can see that they also commute too. So momentum operators commute too, like position operators. To find the commutation relation between x and px, we need to use it on a function. So xpx on f is x minus ih bar df dx, minus pxx on f, which is minus ih bar d dx on xf. We can write it as minus ih bar x df dx plus ih bar f plus ih bar x df dx. And these two cancel out, and we have ih bar f as you see. So for the position operators and their corresponding momentum operators, it's really different if we first use px or x on the state vector. Now, keep in mind that Lx, Ly, and Lz are components of L, and L squared is Lx squared plus Ly squared plus Lz squared. Now let's find the commutation relation between Lx and Ly. Here we have x, and so after x comes y, and then we have z, and we can write it like this. And for Ly, we have y, so after that we need z, and then x, and we can write it as this expression. So if we have a commutation relation like this, we can write it as a minus b times c minus d minus c minus d times a minus b. Now let's calculate this. We have ac minus ca, then we have minus ad, then we have dA, and so on. And pay attention that here order matters because we're not sure whether AC is equal to CA or, for example, CA is equal to AC or not, if we can actually use them without considering the order or not. So we need to pay attention to this. These two expressions are the commutation relation of A and C. The next two terms are minus A and D. And as you can see, the next one is minus commutation of B and C. And finally, the last expression is B and D, the commutation relation of B and D. So it's like that we are actually doing this to this expression. So to find this expression, we first need to find the commutation relation between ypz and zpx. The next one is ypz and xp, and pay attention that here we have a minus sign. The next one is minus zpy and zpx, and finally the last one is zpy and xpz, and we have two minus signs, so here we have a positive sign. To calculate this one, we need to know the commutation relations between y, pz, z, and px. We know that y and z commute, so we can say yz is equal to zy. Also, px and pz commute, so it doesn't matter whether we use px, pz, or pz/px. For y and p, they also commute, and we can say ypz is equal to pzy, so it doesn't matter. And for z and py, they again actually commute, and we can write it like this. But for z and pz, they don't commute, so we cannot actually change the order of zpz or pzz, and they cannot actually commute. So let's write it down. Ypz and zpx commutation relation can be written like this. Z and px commute, and also y and pz commute, so we can change their order. And these expressions become ypz px minus pxz pzy. Here y commutes with all the three operators we have before it, and also px commutes with all the operators we have after it, so I can take y to the beginning and px to the end. And write this expression as y times pzz minus zpz and times px, which can be written as y commutation relations of pz and z, that they don't commute, and also px. So we can write the first term as what we actually calculated. But this term is 0 because y, pz, x, and pz, they all commute with each other, so it's 0. Actually, the third term is 0 because z, py, z, and px commute with each other, so this is 0. But in the last part, we have one z and one pz that don't commute with each other, so it's not 0, and we need to calculate it. So for this one, we can write zpy xpz minus xpz zpy, and we can actually commute py and other terms that are in front of it and take it to the last actually order. And we can actually take x in the beginning, so we can write it as x z pz py minus x pz z py. And now you can see that z and pz do not commute, and if we actually factor x and py, we can write it as x times the commutation of z and pz and times py. And we find the second expression to be like this. Commutation of pz and z gives minus h bar, and commutation of z and pz gives ih bar. So we can write it as ih bar xpy minus ypx. So pay attention to the cyclic order that we had, and you can write it as ih bar lz. If you do the same thing for other operators, you can see that lx and ly commute to be ih bar lz. Ly and lz commutation relation is ih bar lx, and as you can see, lz lx has the commutation relation of ih bar ly. So you need to pay attention to this cyclic order. If we have x, y, and then z, we have ih bar, and if we have x, z, for example, if you want to find lx and lz commutation, you can write it as minus ih bar ly. So the commutation relation of position and momentum operators are not 0, and also the commutation relations of these angular momentum operators are not 0. But what does it mean? Lx Ly minus Ly Lx is IH bar Lz. So we can write Lx Ly as Ly Lx plus IH bar Lz. And if they act on a state vector, by this expression, extra expression here, we can say how change of order impacts the state. We can write the uncertainty principle for two operators A and B like this. So let's use it for Lx and Ly. It gives h bar squared over 4 times the expectation value of Lz squared. And this expression tells us that we cannot find and measure Lx and Ly accurately. Actually, we cannot measure them to arbitrary accuracy. And these two operators, these two observables, are incompatible. So here we can say that we can't find states that are simultaneously eigenfunctions of Lx and Ly. So let's see if x and Lx commute, and as you can see, they commute because x commutes with y, pz, z, and py. You can do the same thing for x and Ly and x and Lz and find them to be IH bar z and minus IH bar y. We can also find the commutation relation of px and Lx to be 0 because px doesn't commute with y, pz, z, and py. But as you might expect, we can actually say that the commutation relations of px and Ly and px and Lz are not 0 and they do not commute with each other. And they can be written as IH bar pz and minus IH bar py. In classical physics, we use L to show the motion of center of mass, and we can also use LCM, which is the motion about the center of mass. But in quantum mechanics, it's a little bit different. We have a general angular momentum, we have an orbital angular momentum, and also a spin, but it's a little bit different that we're going to talk about in next videos. From now on, we are going to talk about commutation relations for the general angular momentum J. We can write the same expressions for Jx, Jy, Jy, Jz, Jz, Jx like the ones we had for Lx, Ly, Ly, Lz, and Lz, Lx. And we can write J squared as Jx squared plus Jy squared plus Jz squared, and we're going to show that J squared commutes with Jx, Jy, and Jz. So let's find this commutation relation. We can separate it into 3 terms, Jx squared and Jx, Jy squared and Jx, and Jz squared and Jx. We are just using Jx, and we can do the same thing for Jy and Jz. So let's do this for a squared and b to see what happens. We can write this as aab minus baa. So if we add and subtract another term aba to this expression, we can find that this part is a times the commutation relation of a and b, and this one is the commutation relation of a and b times a. For example, for the last term that you can see here, we can set a to be jz and b to be jx and write it like this. So this one would be 0 because jx and jx squared all commute with each other. But for the second term, we can set a to be jy and b to be jx and write it like this. And as we actually calculated before, you can write the last term as this. We know that jy jx is minus ih bar jz, so we can write it as minus ih bar jy jz. For the next term, we know that the commutation of jy and jx is minus h bar jz, and we can write it like this. And for the next terms, we can write it as ih bar jz jy. And finally, the last term becomes ih bar jy jz. And as you can see, these two terms cancel out, and also these two terms cancel out, and we have 0. So we can say that j squared commutes with jx, jy, and jz. It's very important to know jx, jy, and jz, and also j squared are Hermitian operators. So they have real eigenvalues. We saw that j squared commutes with jx, jy, and jz. So jx, jy, and jz don't commute with each other. You know, they can have simultaneous eigenfunctions with j squared, but separately because they cannot commute with each other and they cannot have simultaneous eigenfunctions with each other. We choose one of them for example, jz, and we are going to find the simultaneous eigenfunction of j squared and jz. So suppose that these eigenfunctions, these simultaneous eigenfunctions are alpha and beta, and the eigenvalues for j squared are h bar squared alpha, and also the eigenvalues for jz are h bar beta. We have used h bar squared and h bar because we want alpha and beta to be dimensionless. You know that based on this expression, the dimension of h is energy times time. And it's very important that these eigenfunctions are orthonormal. To find these eigenvalues and eigenfunctions, we need to introduce two kinds of new operators called j plus and j minus, which are called raising and lowering operators, and you will see why. We define j plus and j minus as jx plus ijy and jx minus ijy. So we can write jx as this and also jy as this expression. And also jx squared can be written like this in terms of j plus and j minus, and also jy squared can be written like this in terms of j minus and j plus. Based on these new operators, we can find the commutation relation of j squared and j plus and j minus to be 0 because j squared commutes with jx and jy and also jz. We can write it as jx plus ijy and jx minus ijy. So we do the same thing we did before, and we can find the commutation relation to be this. These two terms are 0. And for the remaining non-zero expressions, we can write this term, and it gives us 2h bar jz, and we can find the commutation relation of j plus and j minus to be 2h bar jz. It's also useful to write the commutation relation of jz and j plus. It can be written as commutation relation of jz, jx plus I, commutation of jz and jy. The first term gives ih bar jy, and the second term is I times the commutation of jz and jy, which is minus ih bar jx. So we find the commutation of jz and j plus to be h bar j plus. You can do the same thing for jz and j minus, and you can find the commutation relation to be minus h bar j minus. Now we are going to find j plus j minus operator in terms of j squared and jz. We can write it as jx plus ijy times jx minus ijy, and you can actually do the calculations. And this gives jx squared plus jy squared minus ijxjy plus ijyjx. Pay attention that jxjy is different from jyjx because they don't commute with each other. We can write it as jx squared plus jy squared minus I and this term, which gives actually jx squared plus jy squared plus h bar jz. We can also find j minus j plus operator to be jx squared plus jy squared minus h bar jz, and I have shown you what has changed to give us this actually expression. Now we know that jx squared plus jy squared is j squared minus jz squared, so we actually use them in this expression, and we can find these two expressions based on j squared and just jz. So j squared can be written in these two forms. And if we add these two equations together, we can find j squared to be this expression, which is in terms of jz and j plus and j minus. Now let's get back to our eigenvalue and eigenfunction problem to find the eigenfunctions and eigenvalues of j squared and jz. We also learned that these commutation relations apply. So, if j plus and j minus act on our eigenfunctions and we act jz on them, based on this commutation relation, we can write it as plus or minus h bar j plus or minus plus j plus or minus jz that can act on alpha and beta. The first term gives this. And for the second term, you can see that jz can act on alpha and beta, and we are left with this expression. So if jz acts on j plus or minus alpha and beta, we can see that it gives h bar times beta plus or minus 1. So this is an eigenstate of jz with h beta plus or minus 1 as its eigenvalues. We can do the same thing for j squared, and you can see that j plus or minus operating or acting on alpha and beta is an eigenstate of j squared with eigenvalues of h bar squared alpha. Pay attention to the eigenvalues of jz when acting on this state that changes beta, but here for j squared it doesn't change alpha. So we can say that j plus and j minus acting on alpha and beta give us a new state, a new eigenstate as alpha and beta plus or minus with h bar c as its eigenvalues. The reason is that when jz acts on this state, you can see that jz can act on this state with beta plus or minus and it changes the eigenvalues. We also know that j squared is jx squared plus jy squared plus jz squared. So j squared minus jz squared is jx squared plus jy squared, which is a non-zero quantity. So we can say that for each alpha, there should be an upper limit for beta. It's because if we find the expectation value of j squared minus jz squared in these eigenfunctions, we can find it to be h bar squared times alpha minus beta squared, and this quantity is 0 or positive, which means alpha should be larger or equal to beta squared. So beta has an upper limit. So if we act j plus, which is the raising operator, on alpha and beta maximum, it should be 0. This operator doesn't give us a lot of information. So instead of that, we use j minus j plus, which is this expression, and we know the eigenvalues of j squared, jz squared, and jz over alpha and beta. So we use this one instead of j plus. So let's use this operator and write it like this, and it will give us this expression, and we can find alpha to be beta maximum times beta maximum plus 1. If we apply j minus on alpha and beta maximum n times, we reach alpha and beta minimum. And if we use j minus on this minimum state one more time, we will get 0. This is because beta minimum squared should be less than or equal to alpha. So let's do the same thing for j plus and j minus, which can be written in terms of j squared and jz. We can find another alpha to be beta minimum times beta minimum minus 1. So we have an upper limit, which gives us alpha to be this expression. And if we actually apply j minus n times on this state, it will give us a lower limit, which is alpha, which is given in this expression. We can liken this situation to a ladder in which the upper steps are alpha and beta maximum with eigenvalues of jz as h bar beta maximum, and the lower limit of alpha and beta minimum with actually eigenvalues of jz to be h bar beta minimum. If we apply j minus on the upper limits, we can find the eigenvalue of jz to be h bar times beta maximum minus 1. And if we do it n times, we can reach the lower limits. Earlier we realized that j minus doesn't affect alpha, so alpha doesn't change, and beta maximum times beta maximum plus 1 should be equal to beta minimum times beta minimum minus 1. This equation has two solutions. Either beta minimum should be minus beta maximum, or beta minimum should be beta maximum plus 1. But the second one is not viable because we cannot a kind of beta that is more than beta maximum, and that is our upper limit. Another equation we can write is beta maximum is equal to beta minimum plus n, because if we act j plus on the actually lower limit, n times we can reach beta maximum. And based on the above solution, we can find beta maximum to be n over 2. For odd n's, we have half integers, and for even n's, we have integers. Let's call beta maximum j and beta m. So alpha becomes j times j plus 1. And we can say all the m's, all the numbers that are representative of our jz, are between minus j and j, in which j is beta maximum and minus j is beta minimum. Now, from now on, we use j and m instead of alpha and beta. And we can write the orthonormality of these eigenfunctions as delta jj prime and delta mn prime. And finally, we have the eigenvalues and eigenfunctions of j squared and also jz to be j and m, and with eigenvalues of h bar j times j plus 1 for j squared and eigenvalues of h bar m for jz. The values that we are allowed to find for j are 0, 1/2, 1, 3/2, which are integers and actually half integers, and the possible values for m are between -j and j. So for each j, we have 2j plus 1 values. So now that we have the eigenfunctions of j squared and jz to be j and m, we are going to use them to see how j plus and j minus change these states. J plus can be written as jx plus ijy, and we can use its dagger and write it as jx dagger minus ijy dagger, and we know that jx dagger and jy dagger should be jx and jy because these are Hermitian operators, and we see that j plus dagger is j minus. So we multiply the equation we have above with its dagger, and then we can find CJM for CJM plus and CJM minus, which are actually the constant we are looking for. We know that j plus dagger is j minus, so we can write the above expression as j minus j plus, which is equal to h bar squared and the actually square of the constant we are looking for. But we know j minus and j plus, which can be written as j squared and jz, and we write it and we know that they can easily act on j and m to be this expression, and so we can find our CJM for actually j plus. We can do the same thing for the minus sign to find jm minus, and you can see that CJM minus can be actually calculated like this. We can write j times j plus 1 minus m times m plus or minus 1 to be j squared plus j minus m squared minus or plus m. If we add this orange expression and subtract it, we can actually group it like this and write the second part like this, and we can also write actually our expression in these terms. So when j plus or minus act on j and m, which are the eigenfunctions of j squared and jz, we have this expression. We have an h bar, and then for the first term, we have j minus m for the plus sign, and we have the minus sign for actually j minus, we have the plus sign, and here we have j plus m plus 1, and here we have j minus m plus 1, and you can see that when j plus acts on jm, we have a new state, which is j. It doesn't actually affect j, but it affects m, and that's why we actually call it a raising operator. And also j minus, when acting on j and m, it actually lowers the state, and we have m minus 1. We can also write jx in terms of j plus and j minus, and write the expression and see how jx affects jm. And also we can do the same thing for jy and write it in terms of j plus and j minus. And as you can see, they have the same expressions because of j plus and j minus. But here the difference is that here in this part we have a minus sign, and here we have I in the actually denominator. But you might wonder how we can find the expectation values of jy and jx in the eigenfunctions of jz, in the actually simultaneous eigenfunctions of j squared and jz. Pay attention to these states and see how jx and jy have actually changed these states, j and m. And because they change j and m, their inner product with jm is 0, and we can say that the expectation values of jx and jy would be 0.